Hello, math fans. Dr. Andy Lovelace. I'm going to make another test prep video here. I'm a little behind here. I'm just showing you my website for my students this term. I think this is less of a priority. No students have been asking me about this, so I think it's not as big of a deal. But I'm making these little collections of old exam questions, which you can click on. And if you just want practice with that stuff, I have solutions posted. Mostly they're from old exams. I promised I'd make videos. I think for the videos, I'm just going to make kind of little, rather than work through the entire problem again, since a lot of people haven't really been asking about this. I'm going to just talk about it a little bit. But I do think it's vital to your success to spend some time looking at old exams. It just makes the homework more real. In an ideal world, we would do the homework, understand the questions before we moved on, and then we would show that understanding on the test. But I think seeing an old exam, and I've added to the exam archive videos on how to study, things like that. Okay, so I'm just going to kind of look at it and say a few things, and that way I can get these videos out to help you. Okay, so this test prep that I made years ago is a collection of things that have to do with the last few things we were doing with vectors and the beginnings of lines and planes. So this first question was about from an old exam, and it was about two things: rescaling and projections. So if you still have some lingering questions on that, orthogonal to both vectors, that's a cross product. So this question was to take the cross product of these two vectors. That's something you want to practice, make sure you're good at, make sure you can check your work. Again, check the solutions for that. So my plan here is to not go through the problem, but point you to the solutions. But you should have a plan of not only how to compute the cross product, but how to check it. Once you get that vector, whatever it ended up being, then it was a rescaling question. And remember, if you want to make a vector have length 7, you first divide by its length, and then you multiply times 7. That's it. The second question was a projection. It's kind of a perfect example of a projection. So let's call this B, and well, I shouldn't call that B because it's already labeled. Let's call that, I don't know, C and D. So this is an example. The question is asking you for this distance. That's an example of a projection. I didn't spend as much time on this in class as I do some terms. I've had quite a few people asking me questions about this. So let's recap. If this is a vector A and this is a vector B, and I want to know this length from here to here, which is the projection. It's the length you get if you form this little right triangle. And if you want the brief recap, it goes really fast. So if this is this length we want, the basic observation is that that length divided by the magnitude of A has to be the cosine of the angle between them. That's where this all came from. And that meant that L is the magnitude of A times cosine of theta. And then in this section, we had a huge fact about dot products that said A dot B is the magnitude of A. I know I'm working in kind of an awkward way, but I didn't intend to do this. And this is sitting right here. So if we divide both sides by the magnitude of B, we get our answer. That L is the following. So the length of the projection is A dot B over the magnitude of B. And I find it fairly easy to remember because the thing you're projecting on, this is the ground, so to speak, which is good because it's the denominator. So I find that easy to remember. So the main things to remember is if you want to use this formula, the vectors have to be tail to tail, and you need to figure out what the ground is. Now in this case, that means I'm going to need the vector AC, and I'm going to need the vector AD, and AD is the ground. So we are done. AD divided by the length of AD. Now sometimes students get too excited and they forget to do their subtractions. Before you can start the problem, you do need to get AC by doing 3 subtractions. 3 minus 0 is 3. 1 minus 1 is 0. 4 minus 2 is 2. And then do AD. 2 minus 0 is 2. 1 -2. Then you do the dot product. It's fairly quick. So you're going to do, so this problem I actually could do without much effort. And then you're divided by the length of d, which is, I think, the square root of 9, because it's 4 plus 1 plus 4. So it's going to be 2/3. So ultimately, this is not supposed to be something confusing. It's a nice little side application of the dot product. Now, a few students have said, hold on, there's a second formula. What was that second formula? So what we just did was called the component of AC in the direction of AD. That's more of a physics term. That's not essential for this course. You just really need to know that formula. Now, occasionally we might want to do the same rescaling game we did up here with the vector AD. So how would you do that? So I don't even think of this as a projection, so to speak. I just say, I want to take the vector AD and I want it to have length 2/3. How do I do that? I divide by its length and I multiply by 2/3. That's the so-called projection vector of AC onto AD. So that's not a formula I like. There is several ways that can be written, but that's how I remember how to do it. It's a rescaling. The question didn't ask for that. It just asked for the 2/3. So there's yet another recap of projections. It's always a good idea if you are stumped on something. I have a review for it. If you click on my 12.3 was where we learned the projection. So, the nature of these courses, it's a lot of stuff we're covering. And so that's why I have supplemental things if you need them. And on this review sheet, I have pictures of this and everything. All right. So that's something we sometimes ask as a small thing on a test. The actual projection part would be like 1 point at the end. It's mostly about, can you find the vectors? All right, so then I have a collection of other problems. This is just about vector operations, so we can run through this fairly quickly. Anything in bold is a vector, so it's asking us some understanding questions. So you have to basically go so students that are still mixed up on these ideas, we have a few operations we've defined, a vector dotted with a vector, and we should know that's a number or a scalar, and we know a bit of what it is. A vector crossed with a vector is a vector. We have a number sitting next to a vector, so that would be a scalar with no operation between it. And that's a vector. That's that rescaling. We can add two vectors, vector plus vector. So this is just getting us to think symbolically about what we've defined and what we haven't defined. Okay, so let's see if that accomplishes most of the things we want. So the way you would think through this is, okay, here's a cross product. Are there vectors on either side of it? Yes. Great. What does it spit out? A vector. Great. Then we have a dot product. A vector dotted with a vector. So that's perfectly fine. But what is it going to give? So ultimately we're doing a vector dot with a vector. It's a scalar. All right, let's play the next game. So then we do a dot product. A dot product gives you a scalar. So then I have a scalar next to a time symbol in a vector. That's nonsense. So it's not in the right form. Okay. What is this one? A dot product, which gives me a number, divided by the length, which is a number. So that's okay. That's a scale. It's just a fraction, actually. Number over a number. If you really were mixed up on these, you could just make up an example. Have U be 1, 2, 3. Have V be, you could even have it be 1, 2, 3. And just calculate and see if it makes sense. But you want to get to where you can just see it. So a number over a number is acceptable. What do we have here? We have a number divided by a number sitting next to a vector. That's this one. That's what we're looking at. A scalar sitting next to a vector. That's going to be a vector. Projection. What does a projection do? It's a number. We already know this is a number. This right here is a vector projected onto a vector. It's a scalar. We just saw that in our last example. Lastly, the projection. So we're taking the projection vector divided by length. It's a vector. So that's a lot of those were big topics. Okay, consider the line through the points. Find the coordinates at which the point hit the x, z plane. Hopefully finding a line is something that's very quick for you. 1, 3, -2, plus, 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 t, t, t. And I'm going to use the vector pq. So pq, I'm going to do subtracting. 2, 2, 9. Find the x, y, z coordinates at which of the point at which this intersects the xz plane. So then there's a separate question, which is what does it mean to be on the xz plane? It means that's 0. So we want this to be 0. From that we can solve for t. And then once we know t, we can substitute it in. So that's not too bad. Consider the plane P that contains the point and is orthogonal to the given line. We like this situation. They gave us a point. So immediately we should be thinking they gave us a point. So no matter what, let's get that credit. Y plus 1, z minus 2 equals 0. And now I have a point. I already put it in there. I need a normal. So I'm really hoping that they tell me something about something that's perpendicular to my plane. What did they give me? They gave me a line that's perpendicular to my plane. What do I know about the line? It has a vector that points the same way. And I realize now you can't see what I'm doing. There we go. So they gave me this vector, -3, 7, -1. So that vector points the same way as my desired normal vector, so I can use it as a normal vector. Lovely. Done. At what point does this intercept the x-axis? If you're intercepting the x-axis, then these two things are 0, and you can solve for x. All right. And I think that's it for that test prep. So I was just giving you a little bit of a taste of some cross-product things and the beginnings of lines and planes. All right, hope that helps.